Hello, my name is Michael Pershan. I am a classroom teacher of mathematics in New York City, currently at St. Anne's School. And this is a talk about teaching students to explain their reasoning. Talking about explaining their mathematical reasoning. So there's a solution, and we ask students to say, hey, can you explain why this is true? Or there's a disagreement, and we say, hi, can you explain who's right and what do you think? Or we say, anything. So this is about explanation, asking students to explain their reasoning. And I want to start actually by questioning whether, the title of the talk is, can we teach students to explain their reasoning? Can, but I do want to start with should, because it's not as obvious as some people think. And it's even kind of like a close thing, I think. So let me show you an example that I've seen. This is from the mathematics enrichment program, I think. And it's a very typical way that students encounter explanation, right? So there's a question. It's a totally kind of, you don't need to explain anything to answer the initial question. And then it's like, okay, now explain how Dan could be correct. I paid exactly twice as much as Mark, but I only stayed 10 minutes longer. Students need to explain stuff. And I don't know if this is your experience, but my experience as a classroom teacher is that I often find that students have a very hard time answering those prompts. So I teach younger students, 8 or 9 years old, and I also teach mathematics to older students who are closer to 17 years old. And depending on the year, I teach different ages in that range at my school, which is unusual in the US, but I really like it. Anyway, but all those students have trouble with explanation, really without exception. If you say, explain this, first of all, some students will always raise their hand and say, I don't know what to do here. I solved the problem, but I have no idea how to explain it. And the second thing that some students will do is especially with my younger students, this happens often, I'll get like a paragraph. You'll walk over to a kid and it's like a page full of explanation, and they just kept going. And it doesn't make any sense at all. Or it's rambling, or sometimes repetitive. Sometimes it's kind of, you've gone circular here. It's true because I did the calculation and that's why, and I did it. Sometimes they'll narrate their procedure. What's the point of that? Students don't seem to have a good way to explain this, even though they can answer the questions. I actually had I recently had an interesting experience relating to this with my 4th graders who are 8, 9 years old. And so that class has been studying fractions, equivalent fractions, things like 3/7 is equivalent to 9/21, things like that. And I sent home for homework with them a worksheet that I wanted them to work on at home, and had a range of questions, and I didn't think anything of it. The next morning, these students come into class, and there's a real kind of like clatter and energy as they enter the room. Mr. Pershan, I'm so sorry. I didn't know how to answer the last one. I'd forgotten which question was the last one, honestly. I did my best. I wrote something. I wasn't sure what to do. My dad had to help me. It took me a moment to really realize what was going on as I was being bombarded with these questions from these 4th graders. And eventually I did understand that it was this question over here. Explain why the fractions 10/7 and 30/21 are equivalent. That was the question that did them in. Even though in the previous 3 or 4 questions, they had been asked to actually find equivalent fractions. The other questions were no problem at all, really no problem at all for most students. There were a couple of mistakes, but really in general, my students were able to find equivalent fractions, what are some fractions equivalent to 7/6? Or they were able to say, oh, 4/8 is equivalent to blank tenths. What's in the numerator, or the opposite? 3/4 is equivalent to 12 blanks. What's in the denominator? So those kind of procedural questions about fractions, not the big cause of stress. The big cause of stress was the explanation question, which you might have thought, well, if kids can answer those procedural questions, they must have a way that they're doing it. They must be able to understand it somehow. They must be able to share that reasoning somehow. And that's an explanation. But no, that's not the case. They weren't able to do that. And so if I was going to start making a case against teaching explanation, if I was going to do that, here's how it would go. Well, first of all, It's not necessary. Look at these children who are fully capable of answering these questions, but not able to explain how they did it or explain why what they did works. So clearly it's not necessary. That's the first thing I'd say. The second thing is, not only is it not necessary, but it doesn't go well. Typically, you ask students to explain things and they're baffled. They're not sure how to approach it at all. Or if they do, they're not doing the right kind of thing. They're the rambling responses or the circular responses or the kind of narrating their procedure response. Well, first I did this, then I did that, which is not really an explanation, or it's not the kind of explanation that I'm intending with these questions. And I guess the third thing is that very often you see, I don't know how often you see, but you do sometimes see teachers who abuse explanation. Teachers who refuse to allow students to do things that the students can't explain. So, there's sometimes this surrounds like little tricks like, 15 times 10. Well, you can't just, it's not appropriate for you to go ahead and say 15 times 10 is 150 because I added a 0 there. Can you explain why? And maybe students aren't ready to explain why yet for various reasons. Maybe it makes more sense at this stage for them to, just handle the procedure. Maybe it'll be easier to study this other explanation thing later, but there's this pressure some people feel that students should be asked to explain frequently. And there's explanation shows up sometimes on standardized tests in inappropriate ways. The case against explanation would be, it doesn't go well for kids, it's not essential, and can be abused. That's the case I would make it. The anti case, the no explanation case goes like that. Okay, end of talk. We're done. I think that explanation is valuable. So, I'll give a defense now of why I think we should teach explanation, why we should ask students to explain, why we should value this aspect of teaching mathematics. And I guess the first thing has to do with mathematics itself, which is mathematics itself is an explanation-heavy endeavor. Here, this is from Paul Lockhart's essay, A Mathematician's Lament, which is a diatribe against the way mathematics is typically taught. Some parts of this resonate with me more than others. This part, I think, does resonate with me. He says, mathematics is the art of explanation, which I know what he means there. Especially at its higher levels, mathematics is focused on proof, theory building. It's very abstract, and it's only valuable to human beings to the extent that we can explain what's happening to other human beings. A solution that only one person can solve is worthless. And I deepen this to go beyond just the narrow confines of research mathematics, but even in school, the joy and pleasure of mathematics that all mathematicians have, whether in school or in general, I think comes from making meaning, being able to say, hey, this makes sense to me. I understand why this is the case. There's something real and there's a way that students connect to what's happening in class beyond just solving the problem when they can explain it. It feels powerful. I understand this. And students will sometimes raise their hands and say, wait, this doesn't make any sense to me, which is a way of expressing explanation is important. And if it's important for us to give to students, I think it's also important for them to be able to provide in a less sophisticated way. They're students, not teachers, but it's powerful and empowering to give students the ability to explain what's going on. I just believe that. I think it's true about mathematics as a discipline, that's one of the things that people like. But I'm rambling a little bit here. And I think if this was it, I might not give a talk about how to teach explanation because, there's all those negative things that I said a second ago. But fortunately, I think this is a case where if we do it right, in a way that kind of avoids some of those negative things, we can get the benefits of both the mathematics as a discipline, mathematics as the art of explanation, along with helping students learn those procedures, not get frustrated, be able to explain in meaningful ways that doesn't feel like you're wasting anybody's time. So that's what this talk is about. Before going any further, I just want to kind of give an outline of how we're going to spend our time here. So I'm going to ask 4 questions and I'm going to attempt to answer 4 questions. The first question is, do students who can explain the mathematics, do they do better? That's the kind of the burden I just gave myself a moment ago, that it's not just about mathematics being the art of explanation, which I think is true, but is it also true that it helps them solve problems, learn procedures, develop their skills? Okay, the second question then is, what does a good explanation look like? If we are going to try to teach it, we should have some sense of what it means for an explanation to be good. I kind of offhandedly criticized kind of these rambling explanations a moment ago, but what's a good one look like? And why is it so hard for students to give good explanations? Why is explain why such a terrifying question to my fourth graders and to many other students? And then finally, in some ways, the most crucial part. So when we get to the classroom, what are the techniques that actually help? And because I don't want to be coy at all, here are my answers to those questions. First of all, do students who can explain do better with skills? Yes, because I think that your ability to explain interacts with your ability to self-explain. And I'll talk more about that very soon. What does a good explanation look like? I think it connects particular things in a solution to general principles. This is an idea I get from research, and I'll share that in a moment. Why is it so hard for students to explain why? Well, here's my answer to that one. I think it's hard to create chances for students to practice. Explanation is harder. It's harder to generate easy practice opportunities for students compared to problem solving. And finally, how do we help kids practice explaining? Well, that one I'll have to share some ideas soon enough. Okay, and that's going to be the whole talk. Warning: I'm about to talk about self-explanation, which I'm going to bring some research. I don't think it's a good idea to read the following slides as I'm talking. They're really just there in case you want to look them up later, or in case there's one aspect of it that I want to highlight, but don't try to read it. Okay. So the question is, do students who can explain do better in other ways in math class beyond just engaging in the art of explanation? And I said yes, because of self-explanation. Now, self-explanation is, I think, a really robust learning technique. It's been researched heavily in a lot of different contexts, starting back in 1989. These researchers over here found that students who were reading worked examples, studying and trying to learn from worked examples, they came to believe that students did a better job learning from them, developing generalizable, transferable ideas from them, if they explained the example to themselves as they were studying it. So self-explanation is explanations you offer yourself as you're learning something. Now, a good question is, what does that mean? Does that mean that you are literally explaining it to yourself in full, complete sentences? Does it mean that you're just providing very careful attention and making sure that you can follow each step? This was not really clarified at the outset. And as people went on researching self-explanation, it got a little bit messy. But in brief, this is a more recent article. This is from 2017 with three researchers: Bethany Riddle-Johnson, Abby Lower, Kelly Durkin. And this is a meta-analysis, and this is a review of the self-explanation literature. I think it's really held up. This is an instructional technique that's really held up, asking students to explain themselves, to make sense of new information, has benefits to students. But they point out that that students don't always know how to do this. So it's kind of like a little bit of a trap. Okay, students who self-explain learn better. Great. But students don't always know how to self-explain. They don't always know how to offer good explanations to themselves. Okay, so how do you teach students to self-explain? So what I'd posit is that going back to my initial question, one benefit of explanation, asking students to explain why, to helping teach students explain themselves better in class, one benefit of that was that it'll enrich their self-explanation. It'll make it easier for students to apply those explanations to new information that they're encountering. They'll have a better understanding of what an explanation looks like. They'll have a sense for what it means to have a satisfying explanation that you've generated yourself. And when they're providing self-explanations, they'll use that as a model. Or maybe they'll even use some of the principles from those explanations in their own explanation. So my thought is that explanation is important because mathematics is the art of explanation, but also because it'll support self-explanation and therefore support more learning. That's my idea. That's my argument. That there's kind of this reciprocal relationship between explanation and self-explanation, that they're really not so different. They're really just, as you explain to others, or if you respond to explanation prompts that you've practiced, that you've learned how to do, that'll also enrich your ability to self-explain. This, I think, follows from some of the research about self-explanation, about teaching students to self-explain, as I'll talk about later, but it's not, this is me. This is not a direct research result. This is an argument that I'm offering. Okay, so do students who can explain do better? I would argue, yes, they do, because of self-explanation, that when we work on explanation, we're also working on self-explanation. Okay, but what does a good explanation look like? I argue that it connects particulars to principles. There's an interesting story here, which is that self-explanation started 1989 through the 90s, the early 2000s. And it took a while for people to realize, this happens in research sometimes, that even though lots of people were talking about self-explanation and studying it, they weren't always talking about the same thing. So this is from more recently. This is from Renkel and Eitel. I hope I'm pronouncing the name right. And they say, I've highlighted this passage, that it's highly probable that different types of self-explanations have different functions. That different types of self-explanations that have been studied by researchers aren't all doing the same thing. And this is, they're coming from a difficulty in defining self-explanation. It's also coming from a difficulty in figuring out, wait one second, this researcher calls that a self-explanation, but is this a self-explanation? I don't know. There were some researchers who were saying self-explanation specifically don't need to be real explanations. They're something more nebulous. They're kind of a super attention, or there's just kind of a, I don't know, a kind of a directed attention that's offered to something so that it kind of clicks, but it's not the same thing. It doesn't need to be verbalized. It never needs to be verbalized to yourself. Other people were insisting that it needs to be verbalized. So it's very confusing territory. Renkel and Eitel say, all right, so I'll say something I think very sensible, which is that maybe there's just different kinds of self-explanation, and different sorts of self-explanation do different things. Now, they don't provide a full taxonomy. They don't list all the different types. I think it's reasonable to say maybe one sort of self-explanation comes from like really paying attention and noticing when you understand things and when you don't. So it's kind of like a self-regulation of attention. Maybe that's one kind of self-explanation. And maybe another kind of self-explanation really just has more to do with memory. Maybe it's just about, well, you know, if you say something and you articulate a full sentence and connect this new fact you've learned, this fact about, I don't know, about this chemical bond, you say, oh, well, that's just the same alcohol from cars. Ethanol is the same kind of alcohol. It's the same. Here's why it's alcohol there, and also the alcohol that people drink. And you've somehow made this kind of semantic connection. You've just strengthened a connection. So maybe sometimes it's about directing attention. Maybe sometimes it's just about, I don't know, remembering, being like, oh yeah, I can remember that, you know, these things are related, and here's why. But that's not what these folks say is the self-explanation that they are most interested in for mathematics and science. So let me share what that is. So what they talk about is principle-based self-explanations, principled self-explanations. Now what this is there's a specific solution, there's a specific instance, and it's connecting it to a generalization. So that's what they call principle-based self-explanations, and that's maybe what it means to offer one thing it can mean to offer a good explanation in mathematics. And that's what I'm going to focus on, these kind of principled self-explanations. Now, the benefits of this, according to these authors, is that it helps with procedural learning. Here's how. If you have studied a particular solution or you know how a particular problem is solved, you might have a hard time generalizing to a brand new problem that's different in some way. If you've articulated, or if you understand a general principle, you can connect these problems. So you can take away from this particular thing some generalization that is then applicable to further cases. So this is the idea here, is that these principled explanations, unlike the other types of self-explanation, are really mostly about generalization, generalizing. So let me give you some, this is a little bit fuzzy, so I wanted to pin it down a little bit. So here's the question that I asked my students before. Explain why the fractions 10/7 and 30/21 are equivalent. Now you might pause here, You might pause in a second. You might pause here and ask yourself, okay, can I give an explanation for this myself? Can I generate an explanation of this? And can I make sure that my explanation is a generalization, something that's always true? Not just something that's true about here, but can I take these numbers here and connect it to something that's true for a much broader category of problems? And you should pause here if you want to. Okay, and now let me share what I came up with when I did this. So I think a not principle-based explanation might be if you draw each fraction as a picture, you just happen to see that they're equal, which might be true, and certainly shows some understanding, potentially. But I think that's not principle-based. I think a principled explanation might go like this. Oh, you can multiply the numerator and denominator of one of these fractions 10/7, what was that, 10/7? Yeah, 10/7 by 3, and you can get 30/21. That's what it was, right? So that is not just going to apply to this specific instance. That is generally applicable. That will apply to the next fraction problem that you come across. So it's useful in that way. If a student can explain this specific problem in those terms, that will potentially help in many other cases. And if a student encounters a new situation, for example, dividing both numbers in a fraction by the same number, they'll be able to adapt this explanation for that case. There's a better possibility that they'll be able to self-explain or explain that other procedure using this principle as a model and a beginning. So basically, I'm making two arguments here. The first argument is that the principle-based thing will help them learn more procedures. I'm sorry, that will help them apply this procedure to other problems. That's a benefit of understanding a principle-based explanation. And the other argument I'm making is that when they self-explain in other cases, they'll be able to use this both as a model of what an excellent explanation looks like, and also, and thereby get the benefits of self-explanation there. And then also, maybe it'll just be the raw material. This is like, oh, well, there it's multiplication, but change one little thing. It's just dividing by the same number. So let me show another example here. So this is from Math by Example, an excellent resource full of worked examples and explanation prompts by a group named SERP in the US. And here's a worked example, a correct one. 56 divided by 8 is 7. Now the prompt in this worked example for the student, to the imaginary student, is explain your thinking, the dreaded explain your thinking. But here's a model of it. Since dividing by 8 is the inverse of multiplying by 8, I use my knowledge of multiplication to help me solve the division problem. We might pause here and ask whether that's principled. I think it is. I think it's totally principled because it connects the specific numbers in this case to a widely applicable principle. So let me articulate that. Dividing by 8 is the inverse of multiplying by 8. That is a widely applicable principle that it will be useful for a student to apply in many other cases from algebra on up. Not principle-based would be valid, but also having no principles present. So I know 8 times 7 is 56 is in some sense a good explanation because it's clearly provides kind of evidence of thought, and it gives you a sense of how this person figured it out, but it's not an articulation of any general principles that might be useful to the student beyond this specific case. We're not articulating anything explicitly that might be useful for later. So I think that's not principle-based, though valuable maybe, and maybe it satisfies one of these other kinds of self-explanations, but I don't think it's what we are going to call a good explanation here. And good's cheating a little bit, because what was to say good, but good for this specific kind of thing, for making generalizations and helping further learning. Here's a final way to just kind of pin down what we mean by principle-based. This is from Illustrative Mathematics, another US curriculum resource, is also open and free. The question here is to match each exponential expression with an equivalent multiplication expression. A lovely task, I think. Write 10 to the negative fourth times 10 to the third as a power of 10 with a single exponent, which is what I gather you folks in the UK call index. We call it exponent. Mostly, I go with the UK in terms of, when you have a term that's one way and we have it a different way, I think usually you're right. I like exponent though. That's just my opinion. So be prepared to explain your reasoning. And this is tricky, but what would a principle-based explanation look like? You might pause again and ask yourself that question. And here's the answer I came up with. When you multiply numbers that have the same base, you can add their indices. If a student was applying that here, a good explanation that uses that principle would be, when you multiply 10 to the negative fourth and 10 to the third, you can add -4 and 3 because the bases are the same. That's connecting the specific situation to those principles. Not principle-based, but still valuable, would be something maybe like, it's like you're multiplying a little, but you're dividing more. Now that's wonderful. And maybe someone would make the case that there's a principle lurking in there implicitly, but it's almost like a different kind of self-explanation. It's making sense of something with maybe like a little bit of an analogy, but it's going to be hard to take that and apply it to a new problem. It's going to be hard to kind of, if you think that and make it explicit and talk about it and come up with it or understand it when someone else says it, that's not necessarily going to help you with 3 to the 5th times 3 to the negative 7th. Maybe it will, maybe it won't, I don't know, but it's not a principle that you could apply as directly. So I'd make the case that you're not getting the benefits of this kind of self-explanation if you're not principle-based. And that's my case. My case is a good explanation looks like that. That's what we should be aiming to teach. Students should be able to generate those kind of explanations for things that we've studied, because it'll help them apply their skills to more types of problems, transfer their skills to more types of problems, apply them to more types of problems. And it'll also serve as a good model for when they're self-explaining things. Well, with that said, what makes it hard? This is reasonable stuff. Why is it so hard? Students learn all sorts of hard things. And I'd like to make the case that the reason why it's hard is because, unlike the problems themselves, where we can just generate lots and lots of, sure, we're doing 10 to the 4th times 10 to the negative 6th. Here's 3 to the 7th times 3 to the negative 3rd. It's just swapping out numbers. I can do it all day. I do it all day. We all do it all day. It's just changing numbers. A computer can do it. A computer can just give you a random problem. It's that simple to generate good practice problems. Whereas explanation questions, they're trickier. They're semantic. They're languagey based. Subtleties will make the questions impossible or easy or trivial or nonsensical. It's not easy to generate practice opportunities. It's easy to explain things to students, and that's good because you're providing an explanation. I shouldn't say it's easy to explain things to students, but in a classroom, we explain things all the time to students. They understand our explanations, but it's much harder to generate explanation opportunities. We can always ask students to explain why, and if they remember what we said, that's good. But as we know from teaching other aspects of mathematics, that's often not enough. Often you need something in between. I heard saw my teacher do this, and doing it totally on your own. You need things in the middle, scaffold practice. And that's what is, I think, the hard thing about explaining why. And that's where I think it's worth us thinking about how we could expand the repertoire of classroom practice for that, for scaffolding, scaffolded practice for generating explanations, okay? So something before, go ahead and explain why this works, but after having learned an explanation from a teacher, how do you practice this? So that's what the rest of the talk's about. I'm not an expert at this at all. I've been working on this in my teaching, I'd say for a year and a half, since I read some of that research, I've been thinking about it more. So it's relatively new to me. This is what I have so far, mostly inspired from the research that I read and from other resources. So I'll share what I have. I'll end with some questions. And I put my Twitter handle at the very beginning of this talk. Be in touch with me if you have other ideas, basically. So let's do it. My journey here started from this Riddle-Johnson paper, and also the Renkel and et al. Paper that I shared before. They end their review of the research with something that I think is really helpful. 4 guidelines for teachers that I'll draw, or for mathematics educators, that I'll draw on here. And their first guideline is, actually, I pointed to this earlier where I was pointing out that students don't always know how to self-explain. And their response to this is scaffold high-quality explanations or structure self-explanation responses. And this is for self-explanation, but I think there are ideas that they share here of having structured responses is good for practicing explanation also. So there's a little bit of a appropriating of this for slightly different goals. This is from the Renkel et al. Paper. This is a technique that they use a lot for self-explanation, but there's no reason why we couldn't do this to practice explanation in class. It's a fill in the blanks thing. So now this is an example from their paper. This is a probability problem. And they ask, why do you calculate the total possible outcomes by multiplying? And what they've left out are just the specifics, the numbers, which is fine. Their goal here is not to scaffold students providing these explanations by themselves. Their goal here is just to make sure that students are deeply thinking about the explanation and connecting it to the specifics. So that's good. So each of the blank initial events, 1, 2, 3, 4, 5 initial events, 5 helmets can occur in combination with 4, I guess, other events, 4 remaining helmets. And they're just going to fill in the numbers here. This is a larger version of this, so it's easier to see. We might leave out more significant things, though, if we wanted students to practice explanation. And I've done this in my teaching sometimes. Desmos is a curriculum company in the US also. They also make this wonderful calculator. Many digital resources that are excellent. And this is from one of their preview lessons from their curriculum. It's a free preview lesson. And they've left out some more significant blanks than in the Renkel et al. Example, right? Every angle inside, 2 polygons are similar. When every angle and polygon on one side has okay, we're asking students to generate something significant here, I guess, a corresponding part in the other polygon. All pairs of corresponding angles have, I guess, the same angle measure. Corresponding sides are related by a single, I assume, scale factor. Each side length in one figure is multiplied by the scale factor to get the corresponding side length in the other figure. That'd be hard if students were if this was their first encounter with this type of explanation. I don't think it's intended to be here. It's clearly not, actually. But I really think it's a great follow-up question. This is a really nice structure. So a bunch of fill in the blanks that are asking students to recall a previous explanation, generate it themselves, not all of it, but some of it. And you can imagine leaving fewer blanks or more blanks, depending on where students are in their learning. And then asking them to explain that to another problem. I think that's really smart. There's an application, basically. Are these pairs of polygons similar? Explain how you know. I think students will be better prepared to do that explain question now that they've been reminded and had a chance to recall the explanation that had been in previous classes or earlier in the class in those fill in the blank problems. I really like this. I think this has worked well when I've done it in class. So this has worked well for me. So this is one robust kind of technique. It connects nicely to faded scaffolded practice for procedures also. So if you're into fading, which I'm not going to talk about that so much here. I Google it, but faded practice eliminates steps from a procedure in a worked example and asks students to generate more and more of them on their own. Eventually, students performing the whole solution on their own. This is kind of like that, I think. It's in the same spirit of that, but in the direction of getting kids to generate principles, widely applicable principles. Oh, similar polygons always have corresponding congruent angles, and all the sides are always related by a single number, multiplication. I think this is really nice. So this is the first technique that I wanted to share. The second technique I wanted to share, oh, oops, this is, I included the same picture twice, but I apologize. It's multiple choice. So this is from a website, another American website, Delta Math, which has got a large bank of digital questions for various skills. And this is a triangle with a single missing angle, angle A, and it says the measure of angle ABC is equal to blank because they are blank. And I think this is multiple choice because when you can click in this digital environment, there's choices. And this I've seen work quite well. Of course, you have to be thoughtful about the choices and where your students are in their process. But without these choices, I've seen students do the rambling thing quite a lot, especially in geometry for whatever reason. Well, I think because students have a lot of intuitions and prior thoughts about shape, but not all of those are in the language and form that we care about in a geometry class. Care about is putting it harshly, but that we're interested in often in a geometry class. So constraining the choices can, I think, be very helpful for students and help them focus on providing the finer details of an excellent generalizable mathematical principle. In this case, well, I don't know, I have to look at the other drop-down menu, but there's what is angle ABC equal to? I guess BAD because of alternate interior angles, though potentially there's lots of congruences here. But anyway, I've done this in my own teaching sometimes. Sometimes I've made it harder by, first of all, giving only two choices, but making them kind of both plausible. So which best explains why angle B, which is an inscribed angle here, is 40 degrees. Option A, isosceles triangles contain two equal angles. Option B, inscribed angles are half the degrees of their arc. I would say that when I taught this in class, option B was the stronger explanation, though maybe option A is also a generally applicable principle, and maybe somebody would find a clever way or to connect isosceles triangles to this. And as a matter of fact, what's happening in this case is deeply related to isosceles triangles. But these kinds of choices, what I like about them is they're both good generalizable principles. So as students are thinking about this, about what best explains this, they are thinking about two principles that will serve them well in the future. Both of these are true, and both will help them solve future problems and provide future explanations. They're good principles. They're both true. So this is another way that I've done multiple choice explanations in my class. I've also sometimes been I've provided options where there's a clear right and wrong choice. So in this one, we're relating cups of water to number of lemons. And in the worked example over here, I'm indicating that this student has found out that you can multiply 8 by 0.75 to get 6, 4 by 0.75 to get 3, and in fact, all the cups of water by 0.75 to get the number of lemons, and also 18 can be multiplied by 0.75 to get 13.5 and answer the question that was asked. And I've also shown that 0.75 came from 6 divided by 8. So that's called the constant of proportionality often. To find the constant of proportionality, we first found 6 divided by 8 is 0.75. Which of the two reasons best explains why? In a proportional relationship, the ratio between the columns is always the same. That's a true generalizable principle. In a proportional relationship B, doubling the entries in one column require one to double the entries in the other. A is clearly involved here. B is true, but not involved here. By the way, I do what I found with the multiple choice things. The reason why I'm kind of laboring a little bit to get two generalizable principles that are both true is because I really don't want kids to pick the wrong one by accident and spend 5 minutes really thinking hard about a not true generalizable principle. That would kind of feels like shooting me in the foot here in terms of my goals and in terms of helping them in the future. Not what I want to do. So but I am taking care here to give them a choice between two true things where one is much more applicable. And so that's how I've done the multiple choice thing. That's worked well for me. I'd say the hardest part in the classroom for me is coming up with choices where there's a wrong but true principle. That's the hardest part of this when I'm writing those multiple choice tasks. But I think I really like the discussions that have happened as a result, and I think that when I've done it well, it's worked out really nicely and it helps students with subsequent problems. So I feel good about that. That was also featured in, I lost that paper, but that was also featured as a suggestion. Both these first two techniques were featured in that paper, that review paper about self-explanation as potential ways to scaffold self-explanation. So this is modified from research ideas that you can read more about in that paper. Here's technique 3 and technique 4, which maybe it's cheating a little bit to call these separate techniques. But I wanted to mention here that a lot of our calls for explanation happen in the context of whole group discussions with our classes, where we say, can anybody explain this? Why is this true? And there's 2 research-based ideas that I think that are important to share that relate to certain techniques that I've used, which is that when we call on students to explain why things are right, we should not, at least in the beginning, leave in doubt whether it's right or wrong. We should call on students to explain why right things are right. And likewise, we should call on students to explain why wrong things are wrong. These are principles that were shared in that paper. And the reason for this is we're trying to direct attention, and it can be, I think, really confusing and harmful to students to be asked to explain something, and then they have to be told 5 minutes into a discussion that their explanation was wrong. That's the opposite of the empowering mathematics that Paul Lockhart's talking about. To me, that's frustrating kids. Now, I wanted to share some of the ways that I've had success asking students to do this in the context of discussions. So not like a task that they're being asked to do on paper or anything, but just conversationally, either with the whole group or one-on-one. So I frequently say, yes, that's right. Or I'll say, yeah, the answer is 24. Why is the answer 24? I'll give it away. And when I do that, what I'm trying to do is I'm trying to cut off the doubt. So a pattern that appears frequently in my classes, a student will say 24, and I'll say, great, 24. 24 is right. Why 24? I'm doing a couple things there. First, I'm trying to make sure that if I call for an explanation, it's an explanation of the right thing, not the wrong thing. I'm also trying to give students the confidence. Generating explanations, as we've seen, is hard, and it's often going to go wrong, at least in the beginning stages. And I want students to feel confident that they're not committing themselves to a wrong thing, that they're not gonna, get the rug pulled out from under them. Actually, what you said was you justified a wrong position there. That would mean that they'd be a little bit embarrassing potentially. So I like to set the stage. This is right. Why is it right? This is wrong. Why is this wrong? I ask those questions in those ways frequently to students in my classes. When I need to offer more scaffolding, more support, or when I'm worried that students will offer rambling explanations that don't get to principles that we value in our class for whatever reason at that moment, I'll ask them to use specific words sometimes, and I found that's helpful too. Can anyone raise their hand and use the word tenths and hundredths to explain why 0.9 is equal to 0.90? I'll suggest words that themselves suggest general principles to try to constrain the talk a little bit. Can anybody tell me why we should be dividing both sides by 5 in this case? Can anyone explain, can anyone use the word inscribed angles to explain why this angle is 30 degrees? Those sorts of prompts have been helpful to me. And that's it for me. I find these really helpful, but I'm left with questions. And so I'll share these questions with you. So the first question that I'm left with here is, I'm doing a little bit of connecting the dots here between explanation and self-explanation. I would love to better understand those dots. Is that true? Do researchers find that's true? Do classroom teachers experience that as true? If it, in the absence of clear evidence, is that our experience? I don't know. I'd love to know more about that. My other question is, are there any other clever practice formats for explanation besides the 2, call it 3 or 4, that I've shared? I feel like I'm padding the resume a little bit by calling 3 and 4 separate things. They're really guidelines, I guess. But 1 and 2 are really clear practice formats. I'd love to know if there's more that teachers have come up with. Now, going back to the beginning of this talk, there's maybe many types of self-explanation, and maybe they're valuable in lots of different ways. I would love a completer understanding of what those types of self-explanation are. And likewise, if there's this parallel between the worlds of explanation and self-explanation, I'd love to know what other types of mathematical explanation there are and what functions they serve. I know that there's a lot to read about that, but I have more to understand there. And finally, this is all part of mathematical explanation has a contentious relationship with proof, where proof is incredibly valuable in mathematics in general, but explanation isn't always the same thing as proof. Or is it? I don't know. So I need to sort out, is this proof? Are the things we're talking about here generating proofs? Is it helpful for later generating proofs? My fuzziness about proof and its relationship to explanation is maybe becoming apparent right here. So that's still a question for me. Maybe you have thoughts about any of these things, in which case, please do reach out to me. I'd like to add that this is all, I wrote a book about teaching with worked examples, and self-explanation plays an important, really important part of this book. But everything that I shared here feels like a missing chapter from it. Everything that I shared in this talk feels like if I had put this together in my mind while I was writing the book, I definitely would have included it. It feels important and connected to the issues of self-explanation in ways that I think I've only been starting to realize more recently. The scaffolding explanation feels like an important piece of this puzzle. So if you do check out my book, think of this as maybe an addendum to it. And if you like this talk, maybe think of the book as kind of an extension of this talk, or related to it at least. And that's it. That's all I have to say about any of this stuff. I really enjoyed thinking about it. And if you have more thoughts, do reach out to me. Have a great day, night, wherever you are. Bye-bye.